Okay, so we're going on to using a spectrograph to analyze chemicals now. So when molecules undergo asymmetric bends or stretches, they create temporary dipoles, and that's absorbed by infrared radiation. So I think I get a little bit crazy over here because I check all the textbooks and other videos and other sources, and there's some errors I see sometimes. So apparently that does not, a symmetrical stretch does not create any dipole change. And so some textbooks say that does absorb IR, but it does not. Okay, so the stretches in bonds must create a dipole, and then the infrared radiation absorbs when there's resonating between a positive and negative charge. Okay, and I'll just leave it at that rather than try and understand why that is so. All right, leave that to the physicists. But the physicists are given this. Okay, so we've got more physics, new physics inserted. I initially got very confused about the divide symbol here, but I think because they always use -1, they never use divide anymore. Like they never do per mole. They always do mole -1. They now think they can put a divide symbol in there. I think so. They're meant to be brackets. Okay, that's not a divide symbol. All those dashes everywhere. You probably know that by now. And so just go to your data booklet. You can grab this formula, and you can grab speed of light. That's the speed of light. So you can see if you increase the frequency, you must be decreasing the wavelength. And if you're decreasing the frequency, which is the number of cycles per second, you're increasing the wavelength. So you increase one, you have to decrease the other. So high frequency is a small wavelength, which is the dangerous stuff, and large frequency is large wavelength. Okay, so just be aware of all that. We're just dealing with the infrared range, which is here, 10 to the -4 to 10 to the -6, but it's converted to wave numbers. So it's a different unit for frequency called the wave numbers, pronounced nu. All right, so we're not using per second. We're doing the number of waves in a centimeter. All right, I don't know why physicists love to have so many confusing things. All right, so many different ways to do the same thing. And it's not in your data booklet, which is really sad, okay? It's not only physics, you have to memorize more stuff. So 1 divided by the wavelength will give you the number of wavelengths per centimeter. So how do you do it? So these are the wavelengths, and this is the conversion. So at the smallest end, you're going to get 10 to the -4, and so that can fit, that's how many waves can fit in a centimeter, so that's 1,000. Okay, so if you have a higher, shorter wavelength, that'll be 10 to the -6, and there's 100 centimeters in a meter, so it's 100 times less if you're just using a centimeter, so it'll be 10 to the 4. What's that? 2 times 10 to the power of 2 is 100, sorry, and then that's 10,000. So 100 to 10,000, so that's 100 just outside of that, and a little bit more outside of that. It is, if you check the ranges, they are much wider than that, and so it does agree. They're all in the same ballpark. Okay, so 100 to 10,000 includes the ones we're looking at. So they're the wave numbers for the functional groups we're looking at. So you've got to be able to convert that. Unfortunately, you're going to have to add that to your memorization sheet and make sure you know it before you go into an exam. Okay, so moving on, problem. So if you're absorbing at 6,100 nanometers, what is that in wave numbers? So that's the wavelength. So you've got to convert it to the centimeters, or you don't have to, but I think there's probably an easier way to do that. So 10 to the -9, less, but 100 centimeters in a meter. So in centimeters it's less, so less by 10 to the 2. All right, you've memorized the formula, you substitute that, plug that into your calculator, just double check that you can convert that thing to that thing correctly, because that's going to be a big source of errors for lots of people, plugging into calculators incorrectly, order of operations not being followed and stuff like that. And check that that's reasonable. 1,600, yeah, that's reasonable. That's within these ranges over here. So it looks correct. Okay, so moving on to the actual graphs now. Now we just generally ignore the fingerprint region, which is 200 to 1,400, so sort of halfway to the right-hand side, because they're so complicated and overlapping that we can't really understand them. But if you use up a data booklet or get a computer, an AI, you can see that these guys all have this small double, then these 2 bits here. So small double 2 bits. That one doesn't have it that well. That's the double and the 2 bits. It's sort of there. That's one that's slightly off. All right. And if you look here, really the whole thing's a fingerprint, but this is the one we can actually get information from. You can see these ones are completely different. And these two are not the ethanol. So if you do a comparison of 2 people's fingerprints in fine detail, you can actually use it, but they're unlikely to give you a question like that, all right, because that's just pattern matching. Okay, so what we normally do is we normally just look at stuff over here and really just over on this end, okay, and you'll just use your data booklet and look up the numbers and see which peaks you get. Okay, now IB is special in that they actually tell you whether one's strong or broad or not, but it's not necessarily the case. This is the Australian data booklet, which I haven't changed because I think it's a little bit more insightful not to use this, because you can see it's not strong, all right, and broad all the time, and I actually call it narrow. So the only thing the infrared, I think, is useful in doing, because the other graphs tell you all this information as well, and then they tell this as well. So the infrareds, I don't even know if are needed or useful. They're good for backing up extra data, so more sources to verify things is good. But if you have a look, when you have carboxylic acids and alkanes, there's an overlap. And so instead of seeing 2 distinct bands, you just get one huge one. And they just say very broad. That says very broad, okay? And the reason it's very broad is because the carboxylic acid, they all have this, right? They all have carbon chains in them. It's because these 2 overlap. And that's why it's just one big thing, all right? Whereas with alcohols, there's a distinct gap. There's 3,000, 3,200, right? This one's got slightly different numbers. And so you can see there's a big gap here. Here, there's definitely a gap. All right. So that one's still, and 2 distinct peaks. So these 2 are the alcohols, and these 2 are carboxylic acids. So that's the question that pops up almost every single time in every test, because that's the only thing it's good for, really. They might give you something else that's useless, but you still have to talk about it, because whatever information's there, you still have to talk about it, and it's still backing up probably the answer you already got just from one of those graphs, the mass or the HNMR. So that's the main thing to focus on. So this one here, we have alcohol groups here. So the alcohol groups here, these are alcohol groups linked to carboxylic acids, which is not it. These are just plain alcohol groups, and there's nothing with 3,2000 upwards with just the plain alcohol groups. So we can cross out A and E because that one doesn't exist. We can then look at this formula here and see if that compound actually can form with this. We can see there's 2 oxygens here, so that cancels that one out. All right. What else are we looking at here? We have a reading at 1,700. So if we look for 1,700, that's quite indicative of a C double bond O. And that one had one, and this one does have one, and that one doesn't have one. So that one really crosses that one out. We're less with D. And so these are the key peaks here. This is just not that helpful because it basically is the carbon chain, and so that's not really indicative. So we've been able to cancel that one out to D. Okay, lastly, it wants you to make note of the greenhouse gases and just point out that they do absorb in the infrared radiation range. And so I've just gone to a journal, and you can see quite clearly they're in the 2000 to 7000. So that's the infrared range here. We know it can go up to a bit more than that, maybe 10,000. And so they are in the right range. You'll notice that water is it's probably more intense, maybe not for that one, but definitely over almost the entire spectrum. So water is far better at it. And then the last thing, just looking at how effective these chemicals are. For some reason, they don't want to put. They just want to focus on this one. So this is a. They don't want to talk about how much carbon. It's always there, but they just put variable, but that's fine. Okay, so this one here doesn't have any polarity to it, so it's not very effective. So nitrogen dioxide is far more effective. These ones have polarity to them too, but they sort of didn't want to talk about them. All right, molecules allow more asymmetrical stretches and bends, absorbing more infrared, so that's why methane's not as effective. So its global warming potential is far less. It's also going to break down, whereas the nitrous oxide is there for a lot longer. So 10 times longer, and so it's 10 times more significant in global warming. Okay, so persistent chemicals have a greater overall effect, and things that have dipoles. Allow dipole stretching will have more effect. I think that's what you need to get out of that. So that was from a journal as well. I'm just trying to keep it pretty solid, peer-reviewed. So just as a postscript, there's so much physics and environmental science in it. I think you should at least know that the environmental science, you need a full 2-year course to do this properly rather than just trying to touch on it. We've lost all our biochemistry, which is sort of grabbing all the stuff we've learned and applying it, and we just seem to be throwing in physics calculations and alluding to environmental science but not really understanding it. So just be aware there are counter arguments that, what's the argument for the sun? There is data to show that it's the sun that's causing global warming, whether it's over a short period of time or hundreds of years. And if you have increased temperature from the sun, then you have decreased solubility of CO2. So CO2 goes into the atmosphere. And also water goes into the atmosphere. And the effect of water on absorbing heat is so significant that carbon dioxide means nothing. All right. There's also geopolitical arguments for pushing the greenhouse, for going for green energy. There's also, that's just one Posneg cycle. There's so many Posneg cycles. So talk to the environmental sciences, environmental systems society students. They spend a whole 2 years discussing this properly rather than us sort of alluding to something without properly talking about all the different issues. Okay.